Welcome to qnawire.
So in this problem, we want to reconsider problem 48 using the software. I used Mathematica, but you could use whatever, use the software that again came with the book. But let's see here. So um, if we look at problem 48, we have this kind of complicated, power cycle here. And I didn't redraw in the software redraw the TS diagram, but it's very similar to the previous one. Basically, all of this stuff basically occurs on this boundary. You can barely tell that it's different here. So it comes up on this boundary, and just like this. And again, these things are all pretty much the same out here, but it's just that here this is very exaggerated, so we can see the difference between 1 and 2 and 3 here, because in reality these are all very basically on this line here. Okay, so what I did in this problem is they asked us to determine the optimal bleed pressure for a closed feed water. So the bleed pressure, the closed feed water loop is here, and so the bleed pressure is here. And so it came in, where did it come in at? 3 megapascals. We're bleeding off right now at 1 megapascal. So we're down here in the two-phase region where we're bleeding off. No, actually, in this problem, I remember now, I drew this wrong. We are superheated here. So this point is actually outside. This curve should have come down, more like this or something. So this is actually in the superheated region. Um, but what we'll find out is if we kind of keep dropping this pressure here, we get into the two-phase region. And in fact, we wind up needing to actually do the two-phase analysis at 0.5 to find the optimal, because it turns out that it's actually quite low. So again, we basically same analysis in the software, but now in this case we didn't have to look up find a quality factor at 5, because we knew the entropy and the pressure there, and it was in the superheated region, so we could then look up the enthalpy there without finding the quality factor. But in the software, we needed to find the quality factor. So what I did here is I just looked at the effect of this bleed pressure on various different parameters in the system. Number one, the efficiency. So you can see the efficiency, is, again, this scale, it doesn't change a lot over this range. I went from, what did I go from? I think I went from, let me see, what was my range here exactly? From 20 to 600. So this is basically no bleed, right? Because this whole system down here was at 20 kilopascal. So basically we're bleeding off here, which makes really no sense, since it would just go into the condenser anyway. We wouldn't get anything out of doing that. So that would be kind of the worst case scenario you get, with basically it would just not be would not be a regenerative uh, system. So let's see here. What we can see here is that we get a max. We get a max right in here about 210 kilopascals, which and it ends up to a pretty close to 32.6%. It would be our maximum. And so notice this is actually pretty, quite a bit, comparatively. It's quite a bit lower. Like, it's down here. Again, this isn't really to scale, but you're going to be bleeding off pretty close to the exit of the turbine, because as it drops from 3,000 kilopascals to 20, you're going to be at about 200, so you're going to be pretty close to the exit of the turbine for optimal efficiency. So, and then I looked at Y. Again, that's the ratio. Where do I have it here? The ratio of this, the mass flow of this, to the mass flow in. So basically the percentage of by mass of what we're bleeding off. And that basically continuously increases as you increase this bleed pressure from 20. It's zero at 20 kilopascals because essentially we're not bleeding anything off, right? We're just taking it. Yeah, there's no sense if it's at 20 kilopascals. That's the outlet temperature, the pressure of the turbine. So again, Y is going to be zero there. So that's a good check that your answer makes sense, that it goes to zero at 20 kilopascals, and then it continually rises up. So at 210, right about here, we're bleeding off maybe about 12% of the flow. And so again, as you go up in pressure, you're going to actually bleed off more and more to get the performance, other properties in the cycle. You can also look at other things. I just looked at a bunch of various things here just to see how it affects things. And again, it's not all that, it's not very intuitive, but you can kind of look at these and try to justify the answers. So we can see that as the bleed pressure goes up, our net power output goes down. So let's see what our specific power output was over here. 730, about 738. So here this is in joules. So we're actually, down. We're down, below this. So this would basically continue to drop, I think, as we got. And what was the efficiency we had over here? 31.4%. So again, this would continue to drop, out here as we got to higher and higher pressures, bleed pressures. And I guess we had a Y here too. What was Y? 24%. Yeah, so this continues to increase as we get up to higher bleed pressures. So again, we're getting less and less net work out of our specific work out of our system, out of the cycle as we increase the pressure. But the efficiency is going up because you can see here that the heat we need to put in, the specific heat we need to put in, initially drops faster than the work does, and so that's why we wind up with a peak efficiency, which is the ratio of these two things right around here. I also looked at the quality factor at the exit. Oh, not at the exit, but at the 5 is at the quality factor at the bleed. So I went from basically here up to where it hit the boundary here, and so that was the boundary occurs pretty much very close to 600 kilopascals. So the quality factor goes from at 20 kilopascals. It should be very close to the quality factor. Did we calculate it over here? Probably should have. Yeah, at 6. So 83.6%. So yeah, about 83.6% here. And so then it continues to go up and up and up and up until basically around 600 kilopascals we hit the boundary. And then we would then it would obviously continue to be 1, but then we'd be in the superheated region. So again, this variable doesn't really make sense once you go past 600 kilopascals because it's all going to be vapor. So that's just some analysis of how this bleed pressure. So in the problem, when we're up at a bleed pressure of 1 megapascals, that's pretty far from optimal efficiency, and we could do a lot better by bleeding steam off the turbine much later in the cycle of it losing energy and producing work. So more closer to here.